All right, so good afternoon, everybody. So I'm going to talk to you about like a software stack that's becoming very popular. So I'm going to talk about it in the context of MOM6, since this is Ocean Working Group. But that's something that you could use for like a lot of different ocean or atmospheric models. So if you don't know about X-Array, I hope you're gonna join us and be part of the fun. And if you already know about it, well, I hope you might still learn a thing or two. So what I'm gonna quickly describe is a bit of like the Jupyter ecosystem, X-Array, ZAR, and then what I want to spend a little bit more time on is like that demonstration, because talking about like Python packages and stuff is fun, but it's actually I think more useful to use them and see how they work for real. So first, for those who are not familiar with like the Jupyter ecosystem, the whole thing started with like those IPython notebook, and then became a fusion of like Julia, Python, and R, and so that's where the Jupyter name come from. And so the idea is that you're going to use your web browser as like an IDE, and this IDE is going to communicate with like your interactive Python, Julia, or R session. And so that server side over here can be running either on your local machine, or it can be running on like a remote server, so that can be your analysis machine, or that can be in the cloud. So that's the idea with like the Jupyter notebook. The Jupyter Lab is just a more functional IDE that came after the Jupyter notebook. That's what I recommend. That's what I use. And Jupyter Hub is just an addition on top of that. That's going to be able to run like multiple Jupyter session for multiple people, like on your server. And so at NCAR, you have a good example. You have your own Jupyter Hub, or you can deploy one on the cloud, and that's what the Pangeo folks did with like the ocean.pangeo.io. So next, like a really cool piece of software that's gonna help us like do a lot of science very easily is X-Array. So we're used to think about like our data as being like ND arrays, and then manipulate things based on indexes in your arrays and stuff. What X-Array does is that it adds like labels to all those dimensions. So which means that you don't have to think about, oh, what is the index of my time dimension or spatial dimension? X-Array knows about that. So X-Array was inspired by the data model used like in NetCDF, where like a data set would be like similar that a NetCDF file, and that's a set of like different arrays. But you can also build a data set that spans multiple files. So you don't have that one file, one data set restriction. So your data arrays have labeled dimensions, labeled coordinates, and you can actually use those labels to use methods, apply methods on it. That's going to make plotting or compute more high level. So you're not thinking about indexes. Now you're thinking about dimensions. So I've got two examples that are like pretty simple. One is just like a plot where I just slice a piece of data, and I just tell it, okay, just show me that part, and I don't have to know or care where my dimensions, how how my array is structured or anything. Or same thing, if I want to compute like a climatology, I just tell it to average over the time dimension, and everything happens. I don't have to worry about it. One thing that I'd like to point out, since we're working with like ocean models, is that if you have like multiple set of coordinates, so for example in MUM6, you're gonna have like cell centers and cell corners. X-array doesn't know the relationship between those coordinates. So that's where XGCM become very handy, because XGCM is gonna add that knowledge to X-array. And so with that, you're gonna be able to perform some differentiation or interpolation operations on a staggered grid. So next is Dask. So one thing that's important to understand is that X-array can work on top of either NumPy array or Dask arrays. So NumPy arrays are going to be basically computing eagerly. So once you type your operation in, it's going to execute it. Whereas Dask is going to delay it. And so what Dask is going to do is it's going to build a graph of operation of stuff that it should do, and only wait until the last minute. So when you actually ask for like a result, to actually perform the operation. So you could see that as like a lazy student who just makes like a big to-do list and then wait for the last minute when he has to present something to like do all the computation at once and then show you the plot. So what's gonna make the difference between either we use NumPy or Dask array under the hood is that chunk argument. So if chunks, which are basically the small bits of data, are specified, then we're gonna go into Dask and lazy mode. So when we are like in Dask mode, we can define a cluster, and so this is gonna allow us to do some multi-threaded operations that gonna leverage like all the computing power that we have on our local cluster, or you can build like a Kubernetes cluster if you're on the cloud, or you can submit to a job queue, so your Slurm or PBS job queue with that Dask job queue package. And what's really cool about that is that because we're splitting our computation in like small bits that are like easier for the computer to handle, we can actually work on data sets that wouldn't fit into memory. And that's that OOC for out of core computation that you might have heard or might hear in the future. So one of the things I was looking at too is ZAR. So ZAR is one of those new formats that's also becoming popular, that's very useful for cloud storage. And so we were interested in seeing if that would be a good solution for our needs. So first question, why bother? Well, this has pretty good compression, so that's going to save us a lot of space, and so that's why this is interesting. So it was first designed for like cloud object storage, so whether or not it's a good solution for like more traditional infrastructure is still something we're looking into. What we've seen is that are you gonna cut your data set in like small files or small chunks matters. So the rule of thumb is that there should be around 10 to 100 megs, and I'm gonna make another demonstration later on that. And also there can be like different types of ZAR store. So the most common one is going to be the directory store on your left, where basically every chunk is saved as a file or as an object in the cloud. Or you can also have like a zip store. So for example, on the right, so that .zip file. And this is actually just going to be a zip with like all the little chunks in that. So why I get interested in those zip store? So basically, well, your chunk is one file. So if you take like a big simulation, 3D monthly fields, and you break them down in chunks, well, that amounts to a lot of files. So that's what I get here. And on our system, the number of inodes is something that we have to be careful about. So that's why the zip store is actually pretty convenient, because that turns 26,000 files into one. And so then comes to performance differences. And last I've checked, I've tried to do like the exact same computation on like directory and zip stores, and the performance are similar. So no loss in performance zipping the chunks. So it looks pretty good. One caveat though is that the zip stores are not as commonly used as the directory stores. So there's still like some bugs that you can find, and we worked on like fixing some of those. So now let's move to more of demonstrations. So first I'd like to say that we have that analysis cookbook for MUM6 that is like a community work, and so if you are interested in like X-array and trying to work with X-array, there's like a lot of examples there. If you want to contribute some diagnostics that you haven't found in the cookbook, then please submit a pull request, and we'll be very happy to have your contribution. So just to give like a little tour, this is not very big, is it? Yeah. So there's like different notebooks showing like a little bit of everything, from like setting up your DAS cluster, getting started, time and space operations, and then we move into like more advanced topics like horizontal remapping or plotting, or doing comparison with like observations. So this is that. We're also participating into the documentation for XGCM that I'm going to talk a little bit more in the demonstration. So let's get started with that. Let's make it a little bigger for you guys. Is that all right for you? Okay. Nobody's complaining, so I'm going to go ahead. All right, so I'm going to load a data set that I've got here locally, but Nextcell is the exact same data set on the thread server, so you can play a little bit with it. Little warning though, if you try to run with like the DAS cluster, that's not going to work. And if you try to run it without the DAS cluster, it's probably going to take a long time. So that's the limit on how reproducible that notebook is. So I'm loading my data set. All happen instantly because actually nothing is loaded into memory but metadata. And this is my data set. So it's like some MUM6 half-degree data. Let's look at what I have. I've got some grid metrics, and I've got velocities, temperature, salinity. So first, bad idea that I want to show, and that's going to be an introduction to like broadcasting. So remember that I said that X-array doesn't have an idea of how the different XH, XQ, YH, YQ coordinates relate to each other. So if I try to naively multiply my transport by my temperature, it's going to do it, but it's not going to do it right. And so what I'm going to end up is I'm going to end up with like an array that have time, depth, y dimension, but 2 x dimensions. And right now, it's not hurting anybody, but if I try to like load the data or do some operations, I'm going to quickly run into like a memory problem because that array is like really huge. So that's one example of what you shouldn't do. And that's where I'm going to introduce XGCM, and where XGCM is going to be very useful in our case. So XGCM is going to tell Xarray what is the relationship between those different variables. So for example, here on my x-axis, I'm going to tell XGCM that, okay, XH is going to be the center, and XQ is going to be located to the right of XH. And same thing for Y. And I can also do the same for Z, where in that case, I know that I have one more ZY than ZL, so I'm going to specify it as inner and outer bounds. And I can also tell it that it's periodic in the X dimension. So with that, I can pretty simply create my temperature and my salinity on the U point by using an interpolation function over the axis X. I could do the same for V. In that case, I don't really have a use for it. So let's go with it. Now, my array has the right coordinates. It's on YH, XQ, so that's my U point. So everything's fine. So now let's say that I want to compute some potential density. So my potential density, I don't have a function for it that's X-array based, but I know how to do it, and I've got like an old Python function that I have. So I can use that function, but there's one way of doing it. So I'm going to define that function the same way that I would have done with like NumPy. And so the first thing you think is like, oh, let's just like apply my function on my data array. In this case, that works fine. Why? Because the operations that I'm doing are like simple enough that it's not triggering like an eager computation. But if you're using like functions that are like a little bit too complex, this could trigger like the computation. And if you trigger the computation, then it's gonna build like the whole data set, and that's not probably what you want, and that might not even fit into memory. So there's a solution to apply lazily that function, is to use that apply ufunc. And so apply ufunc is gonna allow you to apply the function in a lazy way. So I'm just gonna do that. That works. So now, let's say, okay, I'm interested in Denmark Strait overflow. So I'm going to take a look, slice along my coordinates to have a quick look at what my region look like. And so from there, I can say, okay, I'm going to take like 23.5 as being my my longitude, where I'm gonna cut, and I'm gonna cut between those two different latitudes. So when I'm doing that, I'm actually selecting the whole data set, and can show how my transport would look like, and that's how it is. So everything like plots very quickly because it just like takes in memory the piece that it needs. So So all of that is like really cool to prototype like some diagnostics and everything. So I had an idea of a diagnostic. That's actually not a good diagnostic, but I'm gonna show it anyway, just for the sake of like computing something. Let's say I want to take like the transport in like layers that are like heavier than a certain density. So I can very easily do that, taking my transport and applying that where function, where I put that condition that the density has to be more than 27.8. And then just sum over the vertical and the y dimension. So once again, the thing is like instant because no computation actually happened. But now I want to see the plot, and I want my computation to go fast. So to do that, I'm gonna spin a DAS cluster on my machine. And so my DAS cluster is gonna return me like a dashboard. And so now I'm ready to run my computation. I'm just gonna start it. And I can take a look at my dashboard to see what's going on actually, and not wait just to see like a line. And now I can see what's going on. So that's my dashboard in action. So it should take only 30 seconds, but I'm afraid that maybe Meet is slowing in the computer a little bit, but it should be pretty fast. So all of those blocks are actually operations. I can see how many bytes I have stored in memory, so that's less than what I have on my computer. And oh, that's it, that's done. And so this is what I get. Again, scientifically, it's not accurate because I'm using like mean velocity with like mean density. So there's like a lot of flow that actually I'm not capturing, but I get my result. And one of the things that I wanted to highlight is the importance of the chunk. So I didn't talk about it much, but when I loaded my dataset, I took that choice for my chunk. So 1 time frame and 35 depth level. That basically does like 55 megs for my per chunk. And so I tried like different combinations. And what you can see is that if you take chunks that are like too big, you can really degrade the performance of your computation because you're taking something that's so big, it barely fits into memory. And so the computer really struggles with it. I don't even know how that one managed to go through. And then there's like a sweet spot. So basically anything between 10 to 100 megs is where you get like the best performance. But then if you take your chunk being too small, then you're going to start also degrading your performance. So here, the take-home message is that it's very easy to degrade the performance of your computation. So always try to think about the chunks and what are the optimal size, and maybe do a couple tests before you deploy something into production to make sure that you're actually using Dask in sweet spot. So that's all for the demonstration, and I'd like to conclude. So what I like with Jupyter is that Jupyter is gonna give you like the same experience whether you're running like on your laptop, on like the cloud, on your HPC system. So it always feels familiar. It's very easy to prototype your analysis and then deploy them in more production workflow. So I'd like to say that Peppermill is something that is very useful for that. Xarray allows you to very easily write some high-level diagnostics, and XGCM is also a companion tool that is very useful, and it adds all that staggered grid awareness to Xarray. Dask gives you like a tool that allows you to do very performant parallel computation, but be careful of the chunking. And ZAR gives you also good compression, but chunking is also important. And what we're trying to do here is like really contribute to like community software and not build like one size fits all monolithic package that does everything that we think you should be doing. But instead of doing that, just like contribute to tools that already exist and like teach to fish instead of like giving a fish kind of idea. So that's all for me.
Great, thanks, Raph. Questions for Raph? A lot of good resources there. Andrew. Oops. Andrew, go ahead.
Yeah, sorry. Yeah, I was just trying to find the button. Thanks, Raph, for that nice demonstration. I think it really ties together a lot of these disparate examples that are out there for how to use Dask and Xarray. One comment and one question. So one comment that I would have is, or I guess partly a question. Are you using like CMIP6 output for these data, or are you using just like output from one of your custom runs?
No, it's not CMIP6 data. It's output for like the half degree that that was published in a former paper. But this could also work with CMIP6 data.
Okay, because that's one of the things I think that I've been trying to convince folks up here at CCDMA to do is to, we have CMORized data, right, CMIP6 compliant data. So to make these examples a little more concrete with, you can just download it just from ESGF, these metrics, and get it all working, I think would be really helpful to kind of spread it. And then the second question I had was, the big thing that's always kind of been a pain for me is to figure out the right chunks. So do you have, and as you saw, there's differences in performance. So do you have any kind of general rules of thumb about what chunk sizes just to start with? So I'm not, spending.
Yeah. What I was saying is that the rule of thumb here is like something between 10 and 100 megabytes per chunk is usually where you get the best results. In my case, you can see like on the notebook, the best performance I had with my chunk being like 50 megs. So I would say around those lines, it's not completely well known what's the best size. So you kind of have to try, and there's a lot of trial and error in that, unfortunately.
Thank you.
Other questions for Raph?
Hey, yes, this is Raph. This is Phil. I have a follow-up on the chunking. So the numbers you mentioned, in your example, you basically are computing stuff reading locally from a file. And if you were accessing stuff through an OpenDAP server, would the chunking go up or down?
So the issue with the OpenDAP is that actually the Dask cluster is not going to work with the OpenDAP. And I think that's because the OpenDAP is serial by definition, and all the distributing computing is actually not working. You can try with the notebook. I've tried several times to get it to work with the OpenDAP, and in that case that doesn't work. So that's still something that's not working properly. But if you were to like compute things, say on the cloud, where everything is like stored like in ZAR with like chunks, you would try to get your chunk size to be also around that 100 megs, so that you can fit a bunch in memory, but not overload your memory, or like have two small chunks that you need to make calls, IO calls that also have like an overhead. So I don't know if that answered your question.
It does. Thank you.
Okay, any last questions for Raph? We put the GitHub, he has a GitHub link in his presentation. We also have copied that notebook to the GitHub site for the webinar series, and that's in the chat box right now. So if you want to play with this later.